Hello, everybody. My name is Eyal Akibi. Today, I will be solving 20 questions regarding optimization, and we will solve them one by one. Those are main subject in the optimization course at Technion. Hope you will enjoy. If you like, have any questions, you can leave a comment. And let's start with question number 1. We're starting with question number 1. As I said, we would want to achieve the first and second directional derivatives. We'll start with the first. Just as a general idea, a gradient of a function shows the direction of the fastest growth of the function. You could see the illustration right here. At point x0, if we derive the function and get the gradient, we'll get the direction of the fastest growth. You see the level sets I've drawn here. And we would want to move in a specific direction, which won't actually have to be the gradient direction. It might be, but we want to derive in a certain direction. This has some impacts on optimization problems. In general, we won't touch this subject at this point, but just for general knowledge. So if we define phi of alpha to be our function f for a vector direction, which is at point x0 plus alpha r. So we actually want to derive it according to alpha and with respect to alpha, actually. And we want alpha to be 0 after we do that. Why? Because we want the direction at x0. That's the main goal. We just want it in a specific direction r. That's why it's a directional derivative with actual respect to r, but we derive it mathematically according to alpha, as you can see right here. So when we derive it, the definition of differential by inner product and stuff we have seen and learned already is the differential is the gradient at x0. That because alpha is equal to 0 after we derive dx. In dx, if we see it, the differential of x, when x is defined to be x0 plus alpha r, which is a vector, obviously, a vector line in some n dimension, would be just, x0 would be a constant because the differential here is with respect to alpha, would just be d alpha r. So the differential of phi would be the gradient transpose, that's by definition of in point x0 times r times d alpha. So the actual gradient, by definition, after we get the differential, would be just gradient transpose x0 times vector r. In more basic math, this is actually the gradient projected on direction r. This is the scalar product. And if you can notice in my illustration, this would be the projection of the black arrow on this blue arrow, which I've already explained, is the directional derivative. So this is an interesting fact and maybe some intuition you could see in this. And now we can move to the second part, which is the second directional derivative. We'll use what we have already accomplished at the first directional derivative. So at this point, we have the first directional derivative in our direction, and we can transpose this to achieve this. And this is a scalar product, which makes it a legal move. And now we want the differential of this. And then what we do is, by the external definition of the gradient, we need the differential of this, and the differential of R transpose gradient is just R transpose differential gradient, just a small movement in the gradient times R transpose. And by the external definition of the gradient, we just get the Hessian times dx, a small movement in x. And x is defined to be dx, actually. Differential of x is defined to be r d alpha, as we've seen already just a few minutes before. And now, when we replace dx with r d alpha, we get this. Which is r transpose Hessian at point x0, because we are interested at the second directional derivative at point x0, just in direction r and not in the direction of the gradient, as I have explained moments ago, times d alpha. And we can write it in a few ways, as you see, by definitions. And by the definition of gradient, okay, the gradient of the directional, like the second directional derivative, which is the gradient in a specific direction of the first directional derivative. Think about it. You can stop the video for a second. It's not so easy to comprehend. Would just be r transpose Hessian at point x0 r. This would be the second directional derivative. So that's the end of question number 1. So moving on to question number 2, which is more a technical question. You will achieve a few tools here and knowledge about deriving multidimensional functions. And just let's just go for it. So we have like f of matrix A times x, which is a vector, as you've seen in the question just a second ago. We define u to be ax, so du would be a dx. So the differential of fu is equal to the differential of fax, since it's an equality we've just seen. So the differential would also be an equality. So the differential with respect to u of f would be the gradient with respect to u of f transpose times du. And that would be, if we replace our variable, we want the gradient with respect to x, we just replace the du, a small movement in u, as we've seen. So du, which is a dx, you just replace it, a dx. So in fact, the differential would be with respect to dx at this point, after this transition, and the gradient is now with respect to x. And we get the inner product by definition of a transpose gradient xf and dx. So by definition, obviously the external definition we already know. The gradient would be, obviously you take this and transpose it, yeah? And like you take this and transpose it and you achieve this. So this is just a gradient. This is the gradient of f with respect to x is the matrix A transposed gradient of x of f. And that would be the gradient. Now we want the Hessian of this function. We use the gradient and we now find the differential of what we've just achieved. So the differential of A transpose gradient f at point ax would be A transpose, which we do not need to differential because it is not, it doesn't have any connection to x, it's not dependent on x. And so we have A transpose differential gradient of x of f. And now what we do, by definition, we know that differential of gradient of x of a function is the Hessian, which would be nabla squared, which is just the Hessian. So what we do is we get A transpose Hessian of f at point ax, just multiplying obviously matrix A times the vector x, a dx. And by definition of gradient, if we want the gradient of the gradient, so we just achieve the gradient, this is the gradient. We just transpose this and we get A transpose gradient squared with respect to x of f transpose at point ax, obviously, times a. So this is the Hessian. So this has been f of ax. Now we will move to a more interesting problem in the second function we have. So if we define a function of a function, notice that the phi here is a scalar function. So we have a multi-variable function which has a vector input and output a vector, and then phi gets the vector it outputted and inputs scalar. So we define h of u to be phi of f of x. So u is f of x, obviously, and the differential of u is equal to the differential of f of x. And like we've seen just a second ago, we get the du is the gradient of x f transpose dx. We will use this soon, really soon, and a couple of times. So the differential of u with respect to h is the differential of phi with respect to u, obviously, since the equality we've just seen. And the gradient of u of the scalar function, we just get the gradient of u of our scalar function phi transpose du, and we just replace du what we have just got. And by using the definition of the external definition of the gradient, we just get that the gradient, which is gradient x with respect to x of h, is gradient of with respect to x of fx, and gradient of phi of fx, its point fx, with respect to x, which we can write more comfortably since phi is a scalar function as just phi prime, as you can see right here. So this is pretty simple, not much into it. We just used in a smart way the external definition to make the gradient more achievable, and achievable in an easier way, better say. And now we have the Hessian. So we have the gradient we just achieved, which we can write this like this, which we just wrote. And now we want the differential of g. So we will use the multiplication rule of deriving, which just, even if it's multidimensional, it's the same thing as with scalar, which you're probably familiar with. So we want to use get the differential of this, which would be the differential of phi prime u times gradient f of x. And the multiplication would say we have to add the phi prime of u with the differential of the gradient of f of x. Deriving this and remembering that phi prime here is a scalar, we just get phi double prime u du, which is just the regular definition we already know, and times the gradient of f of x plus phi prime of u Hessian. Pay attention, this is the Hessian, the differential. We have already seen that, I think, in question 1, 2, and you see it again here. The differential of the gradient would be the Hessian, which is double squared f of x dx. So after we achieve this, we just move on and we replace du, as we've seen, du, this is du, okay? We replace it right here and we get this, which is a scalar. So we have basically the same thing. We just replaced du, and by just simple math, nothing very difficult. If we know this is a scalar, right? So a scalar could be moved to its associative, and we can just move this to be right here. I skip this phase, and by seeing that dx is multiplied on the right on both these terms, we just get this term, you see, and dx is right here. And this means this is the Hessian. So this is the end of question 2. We're continuing to question number 3. We want to get the gradient of, we actually want to derive a trace of x in the power of k when x is a matrix. So we want to find a differential, as we know, and with that, using the external definition of the differential, we'll get the gradient. So the differential of transpose of a matrix in a power of k, let's call x in the power of k y. So a trace, we actually know what trace is. Trace is just the sum of the diagonal elements of the matrix. So if we call xk y, and we just sum it up, and we do differential of this summation, this is the same thing. It's equivalent, and we know that the differential of a sum is equal to the sum of differentials. That's why we can move the differential inside the sum. And by using the same logic and definition we used at the first transition, before the first transition actually, the differential of trace x in the power of k is equal to trace of the differential of x in the power of k. We can actually differentiate before we do the trace function, before we use the trace function. So what we do is we use the multiplication derivation rule, and we just derive each element by its term, each matrix. So it will be trace dx, a small part of x, a small movement in x matrix, times k minus 1 x's. We do the same thing according to the multiplication rule, and we just get very easily that it's equal to the trace of k x in the power of k minus 1 times dx. And by using this rule you see right here of the inner product of matrices, we immediately get the gradient that we wanted, which is k x in the power of k minus 1 transpose. So we're moving on to question number 4. We now want to show that if f is a convex function, the set of all x's when f of x is equal or lower than alpha is convex. So if f is a convex function, we know that by definition, because C is a convex set, that for every x and y, and for a lambda inside the area between 0 and 1, we have that f of lambda x plus 1 minus lambda y is lower or equal to lambda f of x plus 1 minus lambda f of y. So we assume we have two x's, x1 and x2, such that for both, the f of the function value of those x's is lower or equal to alpha, meaning they both belong to the set we are trying to look at. So for some lambda between 0 and 1, we have that f of lambda x1 plus 1 minus lambda x2 is lower or equal to, according to the convexity of f, is lower or equal to lambda f x1 plus 1 minus lambda f x2, which is by definition, according to this line I've just mentioned, is lower or equal to lambda alpha plus 1 minus lambda alpha, which is equal to alpha. Meaning that this point is actually, it belongs to the set that we have mentioned, which is all the x's where their function value of f is lower or equal to alpha. meaning that this point belongs to the set, proves that this set is convex by definition of a convex set. So let's dive into question number 5. We have the norm of a vector, just the norm of a vector, some vector x, and we want to show that it's a convex function, the norm function. So we have this function definition. It's defined from a convex set C to the real numbers. So let's just assume we have two numbers, x and y, two vectors, sorry, belongs to the convex set C. And for some alpha between 0 and 1, we have the following transition. For f of alpha x plus 1 minus alpha y is equal to just the norm of alpha x plus 1 minus alpha y. That's just the function definition. This is just the definition of f, okay? So this is lower or equal by the triangle inequality to this, which is just a familiar inequality. So by using this and using norm properties, we move to this, which is just this expression will be equal, lower or equal than the absolute value of alpha times norm of x plus 1 minus alpha, absolute value, obviously, times vector norm of y. And this is actually just equal to alpha the norm of x plus 1 minus alpha norm of y. And this is actually true because alpha is positive and it's between 0 and 1. So what we get is, if we just see where we started from this, and we just take this, and we see that this is lower or equal to this, we get that by definition, obviously, because the norm of x is f of x and norm of y is f of y, we get that f of alpha x plus 1 minus alpha y is lower or equal than alpha f of x plus 1 minus alpha f of y. By definition, we achieve that f is a convex function. So we're going to see a few tricks, continuing with question number 6. So we want to see that a function, if it has a PD Hessian, it's convex. We're going to use the gradient inequality, which I will show later, just in a second. I'm not going to go through it. There are many proofs online, which might be a little bit easier to follow, but I will show you what I've done to prove it. So for x and y in the domain of f, we have the known Taylor quadratic expansion, which states that f of y is equal to f of x plus gradient of f of x transpose y minus x plus half y minus x transpose Hessian of f at the point x plus t y minus x times y minus x. So regularly, it looks like a normal Taylor expansion, but you should pay attention that there's something really important here, this point right here, that there exists some t which will satisfy the equality of this equality. It's going to be an equality. It's not going to be approximately or something like that. So you should pay attention to that and notice that. So the Hessian of f of u is PD for every u in the domain f. So this thing exactly right here is non-negative. Actually, it's strictly positive because of its PD. So we can conclude that if this is positive and this is an equality, then f of y is bigger or equal than f of x plus gradient of f times y minus x. And this is actually the known gradient inequality, which means that f is convex. And in particular, it's strictly convex, actually, but never mind. I'm just going to go through, just going to show you it. You can pause your video and look about that. the proof of the gradient inequality, which I've done, and it's an if and only if. And by achieving this here, and which is the gradient inequality, we know that we got what we wanted, because F has a PD Hessian and it's convex. So we are in session for question number 7. So we want to show the logic behind the Newton method for multidimensional optimization. So if we have like, as an illustration, the function f here, and we want to minimize it. Let's assume it's like nice and convex, and we will use this assumption later on. There are problems which are solvable when non-convex with all kinds of approximations. This is not the main the main theme of this question. Let's just assume it's convex, and by this we can approximate it quadratically in the following way. In this way, we will find the minimum point in an easier analytical way. We might, usually it works, might not work sometimes, might not conclude to you might not conclude a right solution, or we get to a minimum, a local minimum, but this is the main idea. So we formed the second order approximation with the Taylor series, which we've already seen in the past questions, which is this expression right here, which is f at the point xk, obviously, plus the directional derivative we've already talked about in question number 1, which we already saw in the past question, question number 6. We have the Hessian multiplied by the direction transpose and the direction, and etc. So we use this quadratic expression, and we do assume that the parabolic form according to the convexity I've just mentioned, and in particular closely to the optimal point. So this is the quadratic approximation called the Q of dk, and we want to minimize Q with respect to dk. So we want to derive it and find the condition for best minimizing the direction. We derive it. It's multidimensional, but it's the same way we do it with the scalar, just with vectors and matrices. So if we derive it, this is the way to derive this expression by the way of the Hessian. You could take a look, stop the video, pause it or something, and then continue again when you have agreed with this. So the derivation is this, and the wanted direction for some k iteration would be minus gradient of k times the inverse of the Hessian matrix of the function. So for xk plus 1, we will use this direction, which was given to us by the Newton method, which parabolically or quadratically approximates the right direction for the movement. And we will advance to the next point. Obviously, this is f of xk plus dk. Advance to f of xk plus 1. And from then, we might achieve what we want, or we will want to even minimize it more. This is why it's an iterative method, an algorithm. So xk plus 1 is equal to xk plus alpha dk, which is the normal line search we know. There are many methods. You could read it right here. The Colden section, the Armija rule, and all that, etc. And the main idea of the Newton method, to conclude everything here, is that it finds a good direction for minimization under the assumption of convexity or parabolic form around the optimal point. So that's question number 7. So let's start our debate about question number 8, the Gauss-Newton method for least squares. This is an actually really important problem which minimizes distances. A lot of issues or problems could be translated to minimizing this function right here, minimum x, a vector x, in some subspace of dimension n, a space of dimension n, with this function of the least squares, which is the norm, second norm squared, half multiplied by half. So f is a multivariable function which outputs a vector. And by using the Jacobian notation, we get that fx plus d is approximately f of x, f at the point of x, plus Jacobian, the point of x, times d. It's the linear approximation of the function. Obviously, we see two terms. We know the Taylor expansion. So we'll try to minimize the linear approximation of f, which is actually the main idea behind the Gauss-Newton method for LS. So we try to minimize it with respect to d. So we have this quadratic problem actually, because this expression is squared, and we would want to find the differential of it, just the differential of this, in order to minimize it. So differential of q d, we'll call it q just for the sake of it having a name. So the differential of this expression would be half f k. Just pay attention that I have miswrote the subscript and the superscript about the k here, you see, but never mind, you'll figure it out. It's pretty obvious. Anyway, we continue. So the expression is the differential of this, and this is by definition the norm. If we know the inner product of we know that inner product is the vector times vector transpose, and we know that the second norm is equal to this. Okay, pay attention that this is squared and this had a root and it cancels out. So pay attention, we have moved the differential, and we have effectively used the transpose superscript right here, and this is transpose. This is the transpose of this expression. So we now derive it with respect to the direction, obviously, and then we use the multiplication rule of derivation, and we get the following expression, which is probably pretty easy to figure out after what we have done already. And just notice that we have treated all the d's as we took a little change, a little movement in the d's, and this is just the definition of using differentials. And all the other, like fk or jk, if they're not multiplied by d, which most of the time they are noticeably, are just treated as constants. So the fact is we have two terms, this and this term, while achieving this. So we don't have like any other, we derive the first one with respect to d, and then the second one, and we add them up just according to the multiplication derivation rule. And this is actually a scalar. If you'll look into it, it's pretty noticeably a scalar. This is a vector, small change in d. This is a vector. This is the Jacobian, and this would output a vector. This times this would output this is a vector transpose times a vector row times vector column. This is a scalar. In the same way, this you would see this is also, as we said, this is a vector column, and this would be a row vector. So we get a scalar, we can transpose it, and according to that, we get half of two of the same expression, which is this. And by the definition, the external definition of gradient, we achieve this inner product, and by that we achieve that actual gradient of Q with respect to D, which is the Jacobian of the kth iteration transpose times Fk plus JkD. And this has to be equal to 0. We are actually looking for some extremum point of a function, which is a minimum or maximum, actually. But the general idea, we have to compare it to 0, as we are familiar with this. And we get that Jacobian K transpose times Fk plus Jacobian K transpose Jacobian K times the direction K is equal to 0. And by simple manipulation, we get that the direction of K, of the K direction of D, for solving this problem, the Gauss-Newton method, we want the direction, and then we do perform the line search as we know it. But we want the direction. The correct direction would be exactly this, which is just like moving this to the right-hand side and just multiplying by the inverse of these. And we achieve the direction, and that's the main idea for the Gauss-Newton method for least squares. And by using that and line search and iterating over it, we get each time a different direction, and we minimize our problem and find the objective, which is a minimum point x, which minimizes this. So question 9, next in line. So we will derive the rank-one Quasi-Newton update. We actually want to approximate the main idea, which I will now explain a little bit about and then show. We want to approximate the inverse of the Hessian matrix. We will do something a little bit different. We will compute the Hessian in this method, and then we'll show the same logic for doing the inverse. And this way you will understand how to derive the rank-one Quasi-Newton update. So if we want to approximate the matrix, first of all, just as an idea, we will show at the end how we approximate the inverse Hessian, but just for the first iteration, which sometimes needs a starting condition, we can use I, the identity matrix, or some approximation which we have somehow of the inverse Hessian, just for the first iteration. But the general idea in most cases, we just use I, the identity matrix. So what we will denote is PK, which would be the differences between the current point and the last point, and QK would be the current gradient of point K plus 1 minus gradient of the last point. So we denote this as P and Q, and by definition, we saw in the past exercises, just a few questions ago, that H times the change in the point is equal to the change of the gradient. We saw that you could derive and understand logically from the definition of gradient and from the approximation of Taylor, or it makes sense. You could follow the question we've already done and see that. But intuitively, a small change in the gradient would be its gradient, in so to speak, which is the Hessian times the change in dx, which is the location. Look at it from above. We can use P and Q, and this is not a differential already using P and Q, because this is not a small change. This is not correct by definition already. Because if the difference between the gradients and the points are really far, this might not hold. This would be just approximately right. This is called the secant equation, but we will use it. This does work usually and works well. This actual method is useful when we don't want to compute the Hessian every iteration, and it's much simpler. The next question will even touch the point where this is more useful and less resource extensive. So let's dive in. And if we want to compute H, just the Hessian of the K1 iteration. We want to use HK and add to it something like a rank-one update, just a simple update. So we can call the HK1 update in this way, and we just multiply it by PK, and it's equal to QK, just according to the secant equation. If we develop this equation, we just multiply the Hessian matrix with PK and move it to the right-hand side. And then this is obviously V transpose PK is actually a scalar. We can just divide by it. We get U. But HK was symmetric. We want to keep the same invariant for HK plus 1. So U V transpose needs to be symmetric. And for that to happen, they have to be U and V vectors have to be collinear. So we can just define V to be QX minus HK PK, which we have from past iterations. And we just define HK plus 1 to be HK plus 1 over VT PK V transpose. And that's just the updated Hessian for the next iteration. And we do iterate and through it with the Quasi-Newton method. And this way we achieve our goal and get closer to our solution at each iteration. Just pay attention to something really important, which I mentioned in the beginning. We have the HPK of a QK secant equation, which is correct, but this is also a secant equation which we can use when B is equal to inverse of H. And this is actually the mathematic equation which we are looking for, because we need the inverse Hessian, because we need to achieve PK. It's actually equivalent, but just to put things on the exact way they're supposed to be and done. So using this logic, the secant equation development we have used, and using this logic, we'll get this equation, and in the end, we'll get that BK. You could follow this, it's pretty easy, and it's not, I didn't even write it all because it's just the same thing, but we'll get to BK plus 1 equal to BK plus 1 divided by VT QK instead of PK V transpose. And V is obviously P here instead of Q. It's pretty obvious. And by achieving this, we can iterate and get the right direction at each time and the correct inversation. And with this, we can conclude the Quasi-Newton method for updates. So hold on to your pens. We've arrived to question number 10. We will now explain the idea behind L-BFGS method. This is an idea. BFGS method is the Rank-2 Quasi-Newton method. This is a remark regarding the last question we have just seen. And just as an idea, for a Rank-2 update, we can add more requirements, more properties which we want to achieve when we update the inversation, which is B. So we can ask for an example for BK plus 1 minus BK for some norm W norm to be small. This will actually stabilize the numerical process and make sure they're not too far away from each other. To keep, I rather say, for the process to be numerically stabilized, for this to stay as a PD matrix. So we could, in general, just the idea, you can read on here, but just as an idea, we can add more requirements, and this is the state-of-the-art Quasi-Newton method. So this could work in like twice the size of the problem. We can work on around million variables of problem metrics, million over million, but it's actually not going to be, in the L-BFGS method, not going to be kept as a matrix. This is the beauty in this method. which we can write dk is equal to bk plus 1 gk, but bk plus 1, it's something we have to keep and maintain. This is actually this, but we don't want to hold bk at each iteration and then remember bk plus 1. We want to do just a little bit less. So if we look at it, b0 is probably the identity matrix, probably maybe divided by, not divided by, but multiplied by some scalar, and we can add the rank updates up to now. This is obviously a finite number of updates up to now, up to every k step. K is finite, and then we multiply it by gk. This is the same thing, but written in a bit of a graphic way, though correct mathematically. So we can take alpha and multiply it by gk. This would be this term, this and this. It goes right here. And then we could use u1 and multiply it by v1 to transpose times gk. And we can do the same thing for each update. And this way we get the same thing. We will get dk by adding these terms up to the k iteration, all the ui's, vi's. But the L-BFGS method says something else. I want to remember only the last r steps I've done. This is actually kind of weird. It seems like we're forgetting the updates. This doesn't seem right. But the true fact is that if we remember for some r step, this is some kind of hyperparameter, which we will not discuss and is out of scope at this point. But for some r steps, we can remember the uk, vk vectors and just add the last ones to the alpha I, obviously multiplied by gk, and multiply all of them by gk, all of the ui vi's, which are between k and k minus r. And even though we remember less and it seems less accurate, this works. And this was shown to be effective and can solve problems, a lot larger problems. And this is the idea behind L-BFGS. So we are now heading towards solving question number 11. We will illustrate graphically the KKT conditions, and we can see 3 functions, which is G2, G3, G1, and our function. And this middle point of the level sets, which we can see with the circles, is the minimum point, meaning the gradient is going outside this point upwards, because the gradient is the fastest growth of the function. So normally we would solve this and just want this little point right here. This would be the minimal point. We would be happy and go on with our lives. But we have constraints, and we will now talk about those constraints and how to find a solution from the feasible set. So we can see graphically that this would be the solution of the problem. It touches this level set, and the gradient has to be going outwards. But as for G, the area outside of this curve, which is the level set of G1 function, is positive, and this is negative. This is why I wrote this right here. And going upward, the gradient of G, the growth at this point for G1 would be inside, to go in this direction. Again, with respect to G1, we're not looking at F at this point. We talked about F. So we can see that they are collinear, actually, in the opposite directions. So let's talk about this a little bit in a more formal mathematical way. So G1 is an active constraint, and this will be the best solution. This would be the minimum point of the function, but keeping in mind our constraints. And in particular, remembering that G1
is the main constraint here, because we can see graphically, according to what I just drew, that G2 and G3 are not active constraints. They will not give us the minimum solution for this problem with our constraints in F. G2 and G3 are non-active, and the gradient of F is orthogonal to the level set, which we said, and gradient G is also orthogonal, which we said. And at this point, we know that G1 at this optimal point is 0. It has to be 0 because we defined it this way. So put that in mind. And we get that the gradient of x is worth minus lambda for some lambda from the real numbers times the gradient of G1 at the same point are equal. And just notice, pay attention that this is a minus because we said they're collinear but in the opposite directions. So if we had drawn more constraints which are active, we would have gotten this. This could be drawn and understood pretty easily from the same logic. And this is the sum of all the constraints multiplied by the Lagrangian scalars, lambda I, from the set of indices of the active constraints. So the above function is the gradient of the Lagrangian function, known Lagrangian function, and we would like for it to be equal to 0 to find the extremum points. And we notice that we want like Gx at the optimal point to be lower or equal to 0, element-wise. In this case, the minus gradient of the constraint should look into the same direction of the gradient of the objective function. So lambda star is the vector of lambda i's, which I've mentioned. And for the inequality active constraints, these have to be larger than 0. They can't affect the direction. We already put a minus right here, and making one of the lambdas minus would flip the direction and would conflict with what we have said so far. And for non-active constraints, this could be proved by contradiction. Anyway, this will cause lambda optimal, like the lambda i's scalars, to be 0 for those constraints. So in fact, we get that for this sigma, for the active constraint, Gix star is equal to 0 at those points, because this is how we defined it, actually. And for non-active constraints, the lambda I would be 0. And in general, returning to our problem, we can understand the logic behind this, because for these constraints, the lambda will be 0. It won't work any other way, counting on what I just said. But this constraint at this point has to be 0, because this is how we defined it, and the gradient has to be in the opposite way. So this is the main idea of the KKT conditions. It's a graphical illustration of it, and we touched the math just a little bit. I hope it was understood and pretty clear. And this is a little bit hard to take in. You could look at the video just one more time to make sure you figured it out. We have reached question number 12, the augmented Lagrangian question. We will illustrate it, try to explain what it is and why it is, and let's just dive into this. The augmented Lagrangian is for inequality constraints in one dimension. It's actually a method to make the cost a cost function for each mistake we have done. This is written here actually exactly the same way I just said. We might violate a few constraints. This will allow us to pay a penalty, meaning that important mistakes will cost us in our goal function, and non-important mistakes will cost a little bit less. And we can define a fee for every constraint, and with this logic. So this is like an example in one dimension. We will evolve while talking about this example. Just note for now that we have the function f, which is monotonically decreasing, and we want the minimum x such that for if x is equal or lower than 0, such that the minimum of fx would be the lowest value. So we want the x that will make this value of the function smallest, which is obviously here. So we define phi of x to be exponent x minus 1, and we want to minimize the function, which you've seen in the last, just in the last exercise, which is fx equal f of x, just our function, and the cost function of our constraint, which is phi of x. This is our addition. This is what we want to minimize. By the logic we've built the last question, the method, we need to add this, and we want to minimize the whole thing. If our constraint was irrelevant, this would have been 0, and f of x, big f of x, would have been equal to f of x, and that would be just a normal solution to finding an extremum, in particular minimum point of a function. So this will be minimized when the gradient of this would be 0, gradient of big F, meaning gradient of small f is equal to the minus gradient of the cost function phi. So we see that the point which the slopes, you see, this is the slope at this point, and our function, you see, this is the phi of let's say p at the first iteration. We'll talk about p just in a second. Let's say phi of p is just ex minus 1 for the first iteration. By the way, p is equal 1, and this is actually correct. But never mind, we'll talk about this in a second. The slope of fx and the slope of minus this, and the minus slope of phi of x are equal, but at this point, which won't be the accurate and best solution for our problem, which is this best solution on the y-axis and f, where they collide. This is the best solution. So we can now define a family of function using p. So the family of function of cost function is equal to just adding the p parameter 1 over p times phi p of x, which means just putting e p x minus 1 and multiplying everything by 1 over p. So when p is equal to infinity, phi of p is phi of infinity, which actually will create the situation. You could put numbers in just to get the intuition, but it's pretty obvious, pretty straightforward, that x is feasible and the cost function would be 0, and when it's infinite, when x is not feasible, the cost function would be infinite. And it will be something like this. It will look like this. Is when p grows, the blue line we have just talked about and demonstrated when p is equal to 1. We talked about this just a second. So when p approaches to infinity, we can see that we get this exact thing, and it happens pretty fast when p approaches to infinity, depending on our function. And this is the ideal penalty. And so now we want to find the x, and we can subscript it as p, which is the optimal point for this function, using the cost p function. We can actually iterate over p and increase it until we reach some large p, and the violation becomes more significant with the progressions of iterations. We stop at a large p because of numeric limitations. Our computers are finite, and everything we can handle as human beings. It's finite, and we have numerical limitation. This is why we stop at some point, and hopefully we find the solution before we stop. And in the constraint optimization, just to sum this up, we stop at large P's because of numerical limitations. And this converted problem is in fact a good way to solve this using the P parameter. So we will now develop this just a little bit more. We add the mu parameter, which controls the slope, meaning we're not waiting for P to increase in a way that will eventually find us the optimal solution. Obviously, as P grows, this slope over here will turn closer and closer and closer and closer to the y-axis. And when we stop, we will get a nice solution, not totally accurate, but pretty close to our right solution. But adding the mu parameter will actually control our number of iterations and just create a situation where at the second iteration, we'll already get the right solution, saving us time and extensive resources. So adding the mu parameter controls the slope of phi p mu. So mu is the new parameter. We just want to make sure phi prime of p mu, which is our new function, at 0.0, at the origin, is equal to mu. Meaning our phi p function is multiplied by mu, and we get just the phi p mu function. So we want to solve big F of p mu, as we have already described the cost function using the p parameters and the mu parameters. So we do the first iteration with some mu, for example, 1, and we find x bar, which is actually this, which is not the accurate and correct solution. That's our luck. But using the logic and the mathematical development we've just thought about together, we take the slope at this point, which we found, this exact slope, and we create phi p mu2 in a way that this slope would be equal to this slope, which is a constant slope for fx. Take that into consideration. F of x in this one-dimensional problem has a constant slope, and we just want to achieve it at the origin. This slope at the origin. This is a changing slope, obviously, and if we achieve it at the origin, we will be able to get to the optimal point. So we get that phi prime, and we use the next penalty function where the slope at the origin is obviously this slope we've just achieved. So at the next iteration, our penalty function will be built using this slope, phi prime of p mu1 at the first iteration, meaning we change this. In fact, what we get is that f of x, like I said, has a constant slope. So at the second iteration, we get at the origin the ideal solution for f of x, because the gradient of f of x, which is constant because it's photonically decreasing, would be the same slope we have just reversed engineered, you could say, or we forced it to be the same slope at the origin. Meaning at the second iteration, saving us a lot of time, we already find the correct solution for this problem. So thank you everyone for listening. I hope you enjoyed this and have a wonderful day.